Picture this, a faint glow, a whisper of light that has traveled across the universe for over 13 billion years, carrying secrets from the very dawn of time. This is the cosmic microwave background, or CMB, the oldest light we can observe, a relic from when the universe was just a newborn, barely 380,000 years old. But here's the thing, this ancient light isn't just a static echo of the past. It's a treasure trove of mysteries, each one challenging everything we think we know about the cosmos. From strange temperature fluctuations to unexplained anomalies in its patterns, the CMB holds clues that could rewrite the story of our universe. And today, we're diving deep into 30 of its most puzzling enigmas, each one more mind-bending than the last. What makes these mysteries so fascinating isn't just their age or their scale. It's the fact that they force us to question the very foundations of physics. Imagine staring at a map of the universe's infancy and finding something that shouldn't be there, a cold spot that defies explanation, an axis of alignment that hints at forces beyond our current understanding, or even whispers of other universes lurking just beyond the edges of our own. These aren't just scientific curiosities, they're cosmic riddles that could unravel the fabric of reality as we know it. And the craziest part, we're only just beginning to scratch the surface. So why should you care? Because this isn't just about distant stars or abstract theories. The CMB is our closest link to the origins of everything, the Big Bang, the birth of galaxies, even the fate of the universe itself. By unraveling its secrets, we're not just solving puzzles, we're piecing together the story of us, and that's what makes this journey so thrilling. Whether you're a seasoned space enthusiast or someone who's just starting to gaze up at the night sky with wonder, these mysteries invite you to step into the unknown, to question, to explore, and to marvel at just how much we still have left to discover. So buckle up, because by the end of this, you'll never look at the universe the same way again. The first great mystery of the cosmic microwave background lies in its imperfections. When scientists first predicted this ancient afterglow, they imagined it would be perfectly smooth, a uniform sea of microwave light stretching across the cosmos, just as the early universe should have been. But when satellites like Cobe and Planck finally mapped it with precision, they found something astonishing: tiny temperature fluctuations, variations as small as 1 part in 100,000. These anisotropies, as they're called, reveal a patchwork of slightly warmer and cooler regions, like shadows flickering across the universe's oldest photograph. Here's why that's so baffling. According to the standard model of cosmology, the newborn universe was a hot, dense soup of particles where energy should have been distributed nearly evenly. So why these irregularities? One leading theory points to quantum fluctuations, microscopic ripples in the fabric of spacetime itself, magnified by the universe's explosive expansion during inflation. These tiny wrinkles in the early cosmos may have seeded the vast cosmic structures we see today: galaxies, clusters, and the great web of dark matter that binds them. Without those initial imperfections, gravity would have had nothing to work with, leaving the universe eternally smooth and lifeless, but the plot thickens. Some of these temperature variations don't quite match predictions. Certain patches are hotter or colder than our models can easily explain, hinting at physics we might not yet understand. Could there have been exotic energy fields at play in the universe's first moments? Or might these anomalies point to something even stranger, like the imprint of a universe that existed before our own? What's clear is that these anisotropies are more than just cosmic static. They're the blueprints for everything that followed. Every star, every planet, every atom in your body owes its existence to those subtle variations in the ancient light. And yet, their full story remains one of cosmology's deepest puzzles, whispering secrets we've only begun to decode. Now let's turn our attention to one of the most baffling features in the cosmic microwave background, a mysterious region so cold it defies easy explanation. Stretching nearly 2 billion light-years across, this so-called cold spot stands out like a cosmic bruise, registering significantly cooler than its surroundings. At first glance, you might think it's just a statistical fluke, but here's the catch. The odds of such an extreme anomaly appearing randomly are less than 1 in 50. That's like rolling a die 100 times and never landing on a 6 possible, but so unlikely it demands a deeper explanation. One leading theory suggests this cold spot might be the shadow of a supervoid, an enormous, sparsely populated region of space where matter is unusually scarce. As light travels through such a void, it loses energy, a phenomenon known as the integrated Sachs-Wolfe effect. Think of it like a marathon runner slowing down as they climb a hill, only in this case, the hill is a vast cosmic emptiness stretching hundreds of millions of light-years. The problem: observations haven't found a void large enough to account for the cold spot's extreme chill. Either we're missing something fundamental about how voids behave, or there's another force at play. Then there's the wilder possibility. Could this anomaly be a fingerprint of another universe? Some theorists propose that the cold spot might be the imprint of a collision between our universe and a neighboring bubble universe during the early moments of cosmic inflation. In this scenario, the energy released during such a collision could have left a detectable mark on the CMB, like a cosmic fingerprint smudged into the fabric of space-time. It's a radical idea, but if proven, it would be the first direct evidence of a multiverse, rewriting not just cosmology but our very understanding of reality. Yet for all the intrigue, the cold spot refuses to give up its secrets easily. Alternative explanations range from systematic errors in data processing to exotic physics like primordial magnetic fields or even flaws in our understanding of gravity itself. What makes this mystery so gripping isn't just the lack of answers, it's the sheer breadth of possibilities, each one more mind-bending than the last. The cold spot isn't just a puzzle, it's a doorway challenging us to question whether we're seeing a cosmic defect, a measurement glitch, or something far stranger lurking in the depths of space and time. And that's the beauty of this enigma. Whether it's a void, a multiverse signature, or something entirely unexpected, the cold spot reminds us that the universe is still full of surprises. Every time we think we've mapped the limits of the known, anomalies like this whisper, "Look closer," there's always more to discover. If the cold spot left you questioning the fabric of reality, wait until you hear about the so-called axis of evil, a bizarre pattern in the cosmic microwave background that has cosmologists scratching their heads. Imagine drawing a map of the universe's earliest light, only to discover its fluctuations aren't randomly scattered like confetti. Instead, they appear strangely aligned along a particular axis, as if the universe itself picked a favorite direction. This isn't just a minor oddity, it's a direct challenge to one of cosmology's bedrock principles, the idea that the universe on large scales should look the same in every direction, a concept known as isotropy. The name axis of evil might sound dramatic, but it's fitting for a mystery that threatens to upend our understanding of cosmic fairness. When researchers first noticed this alignment in data from the Wilkinson microwave anisotropy probe, they assumed it was a fluke, a trick of statistics, or an artifact of measurement. But subsequent observations, including those from the Planck satellite, kept confirming it. The chances of such an alignment happening by accident, less than 1 in 1,000. That's like flipping a coin and getting heads 20 times in a row. Possible, but so unlikely it demands an explanation. So what could be causing this cosmic preference? One camp argues it's nothing more than observational bias. Perhaps our solar system's motion through space is distorting the data, or there's an unseen error in how we're processing the signals. Others propose wilder possibilities. Could the early universe have been stretched or twisted by exotic forces during inflation, leaving behind a primordial fingerprint? Some theorists even speculate about a preferred frame of reference, a ghostly relic of physics beyond the standard model. hinting that the universe isn't as isotropic as we thought. Then there's the most mind-bending idea of all. What if this axis is evidence of a larger structure beyond our observable universe? Picture our cosmos as a bubble floating in an infinite multiverse. If another bubble brushed against ours in those first chaotic moments, the collision might have left a directional mark on the CMB like a cosmic scar. It's a radical thought, one that blurs the line between science and speculation, but that's what makes this mystery so thrilling. Whether it's a measurement glitch, a quirk of inflation, or a window into something far grander, the axis of evil forces us to confront an unsettling truth. The universe might not be as uniform as we've always believed. And if that's the case, every textbook chapter about the cosmos's symmetry might need rewriting. For now, this enigmatic alignment remains one of the CMB's greatest puzzles, a silent challenge from the universe itself, daring us to look deeper and question everything we think we know. One of the most perplexing gaps in our understanding of the cosmic microwave background isn't what's there, it's what isn't. According to the leading theories of cosmic inflation, the early universe should exhibit temperature correlations across enormous scales, patterns imprinted by quantum fluctuations stretched to cosmic proportions during that rapid expansion. But when scientists scrutinized the CMB's largest structures, they stumbled upon a startling absence. The expected correlations over distances greater than 60 degrees in the sky simply vanished. It's as if the universe left half its blueprint unfinished, and this missing signature, known as the large-scale correlation deficit, throws a wrench into one of cosmology's most cherished theories. Why does this matter? Imagine inflation as the universe's dramatic opening act, a split-second growth spurt that set the stage for everything to come. In that fleeting moment, quantum ripples should have been stretched into vast, detectable waves across spacetime, creating correlations in the CMB that span the entire observable cosmos. These patterns are like cosmic breadcrumbs, clues to how inflation unfolded. But when researchers compared predictions to actual CMB data, the largest scales fell eerily silent. The odds of this happening by chance, less than 1 in 200, that's not just a minor discrepancy, it's a glaring inconsistency that forces us to ask, did inflation really happen the way we think it did? Some theorists suggest the answer lies in rethinking inflation itself. Perhaps the universe didn't inflate uniformly, maybe it happened in fits and starts, or involved multiple inflationary fields interacting in ways we haven't yet modeled. Others propose even more radical ideas, like the existence of a pre-inflationary phase that left its own imprint on the CMB, effectively erasing the expected large-scale signals. There's even speculation that the correlation deficit could hint at a fundamental limit to the universe's size, a cosmic horizon beyond which our physics simply doesn't apply. But before we overhaul our textbooks, there's a simpler possibility. What if we're just seeing statistical noise? The largest scales in the CMB are also the hardest to measure, with fewer data points to average out random fluctuations. Future telescopes, like the proposed Light-Bird satellite, could settle the debate by mapping the CMB with unprecedented precision, either confirming the deficit or revealing hidden patterns we've missed. What makes this mystery so tantalizing is its potential to rewrite cosmic history. If the missing correlations aren't a fluke, they could point to a universe far stranger and more complex than our current models allow. Whether it's a flaw in inflation, a shadow of pre-Big Bang physics, or just a cosmic illusion, this puzzle reminds us that even our most elegant theories are provisional, waiting for the next breakthrough to either vindicate or revolutionize them. And that's the essence of science, not just answering questions, but discovering which ones we've been asking wrong all along. The cosmic microwave background holds yet another enigma that ties directly into the axis of evil, an odd conspiracy between its large-scale fluctuations known as the quadrupole and octupole moments. These terms might sound technical, but their implications are anything but ordinary. picture the CMB's temperature variations as notes in a cosmic symphony, with each note corresponding to a different scale of fluctuation. The quadrupole represents variations over 60 degrees in the sky, while the octupole covers 45 degrees. Normally, these patterns should be randomly oriented, like confetti scattered without a care. Yet when scientists mapped them, they found something unsettling. Both the quadrupole and octupole appear to align along the same peculiar axis, the very one dubbed the axis of evil. This isn't just a quirky coincidence. The probability of such an alignment happening by chance is less than 1 in 1,000, raising serious questions about whether our universe is as random as we've assumed. Some researchers argue this could point to a fundamental anisotropy, a hidden directionality woven into the fabric of spacetime itself. If true, it would upend one of cosmology's core principles, the cosmological principle, which states that the universe should look broadly the same in all directions. Instead, we might be staring at evidence of a universe with a preferred direction, a cosmic north that defies our expectations. So where could this alignment come from? One provocative idea links it to the very birth of the cosmos. If the universe underwent a turbulent, asymmetric phase during inflation, perhaps due to exotic fields or uneven expansion, it might have imprinted this directional bias onto the CMB. Even more radical is the possibility that these aligned multipoles are echoes of a pre-Big Bang era. Theories like loop quantum gravity or conformal cyclic cosmology suggest our universe might have inherited structures or conditions from a predecessor cosmos, leaving faint fingerprints in the CMB's largest patterns. Imagine finding a message in a bottle, only to realize it's written in the handwriting of a universe that existed before our own. But before we rewrite the textbooks, there's a sobering counterpoint. Could this just be an illusion? The quadrupole and octupole are notoriously difficult to measure accurately, as they're easily contaminated by foreground signals like galactic dust or even our own solar system's motion. Some studies suggest that once these local effects are accounted for, the alignment might weaken or disappear. Yet, even if that's the case, the mystery lingers. Why does the data stubbornly hint at a pattern that shouldn't exist? Whether it's a sign of new physics, a relic of a pre-Big Bang epoch, or simply a cosmic mirage, the quadrupole-octupole alignment forces us to confront the limits of our knowledge. It's a reminder that the universe might not play by the rules we've written for it, and that the deepest mysteries often lie not in the answers we find, but in the questions we never thought to ask. The quadrupole moment of the cosmic microwave background presents a puzzle that's as subtle as it is profound. According to our best models of the early universe, this particular pattern of temperature fluctuations spanning scales of around 60 degrees in the sky should be significantly stronger than what we actually observe. Instead, it's eerily muted, as if someone turned down the volume on one of the universe's oldest harmonics. This isn't just a minor tweak to the data. It's a glaring mismatch that cosmologists call the low quadrupole problem, and it hints that something fundamental might be missing from our understanding of cosmic evolution. So why does this matter? Think of the quadrupole as a fingerprint left by the universe's earliest moments. Inflation, that explosive expansion thought to have occurred a fraction of a second after the Big Bang, should have imprinted specific strengths and scales of fluctuations into the CMB. The quadrupole's weakness throws a wrench into that narrative. It's like expecting a thunderous drum roll in a symphony's opening bars, only to hear a faint tap instead. The discrepancy isn't just academic. If the quadrupole is truly this subdued, it could mean inflation didn't unfold quite the way we've imagined, or that our assumptions about the universe's initial conditions need a radical rethink. One possibility is that the universe is far larger than the portion we can observe. If the scale of inflation's fluctuations extends beyond our cosmic horizon, the quadrupole might appear artificially weak, like seeing only the tail end of a much grander pattern. Another theory points to the shape of space itself. Could the universe be folded into an elaborate topology, a cosmic hall of mirrors that suppresses certain fluctuations? Simulations suggest that a finite, multiply-connected universe could indeed dampen the quadrupole, but proving such a structure exists would require evidence far beyond today's observational reach. Then there's the elephant in the room. What if the quadrupole isn't actually as weak as it seems? Measuring these large-scale fluctuations is notoriously tricky, plagued by foreground interference from our own galaxy and the solar system's motion. Some researchers argue that once these contaminants are fully accounted for, the quadrupole might align more closely with predictions. But even if that's the case, the anomaly has already sparked a deeper conversation about the limits of our models and whether we're missing a piece of the puzzle that's been hiding in plain sight. Whether it's a sign of exotic physics, a quirk of geometry, or just a cosmic mirage, the low quadrupole reminds us that the universe rarely conforms to our expectations. Every discrepancy, no matter how small, is an invitation to look closer and to ask whether we've been listening to the cosmos with ears tuned to the wrong frequency. Among the cosmic microwave background's most peculiar mysteries is a lopsided universe, literally. When scientists mapped the CMB's temperature fluctuations across the entire sky, they uncovered something unsettling. One hemisphere appears distinctly stronger in its variations than the other. This hemispherical power asymmetry isn't just a minor statistical blip. It's a fundamental imbalance, as if the universe itself tipped its hat toward one side during its infancy. The odds of this happening randomly, less than 1 in 1,000. So what could possibly explain why the cosmos seems to favor one half over the other? One leading theory suggests our universe might have a cosmic tilt, a subtle gradient in the density or energy of the early cosmos that left one side more active than the other. Imagine a boiling pot of water where bubbles rise more vigorously on the left side than the right. If inflation, that explosive expansion of space, didn't proceed uniformly, it could have stretched quantum fluctuations unevenly, amplifying wrinkles in one direction while leaving the other relatively smooth. This wouldn't just explain the asymmetry, it'd imply that the seeds of today's galaxies were sown with a cosmic bias, a predisposition we're only now beginning to detect. But there's a catch. Such a tilt would violate one of cosmology's sacred principles, the idea that the universe is statistically isotropic, meaning it should look roughly the same in all directions. If the asymmetry is real, it forces us to ask whether our corner of the cosmos is special, or if we're seeing the shadow of something far more profound. Some theorists speculate this could be evidence of a pre-inflationary phase, a chaotic epoch before the Big Bang where conditions weren't perfectly uniform. Others wonder if we're glimpsing the edge of our observable universe, like standing near a waterfall and sensing the mist of something vast beyond our view. Then there's the wild card. Could this asymmetry be a fingerprint of another universe? In certain multiverse models, a neighboring bubble universe could have brushed against ours during inflation, transferring energy unevenly and leaving one hemisphere subtly imprinted. It's a radical idea, but if true, it would mean the CMB isn't just a snapshot of our universe's birth, it's a family photo with distant cosmic relatives lurking just out of frame. Of course, there's always the possibility that we're misreading the data. Foreground interference from our own galaxy or measurement artifacts could be masquerading as asymmetry. Yet, even after painstaking attempts to account for these effects, the signal persists, nudging us toward a humbling realization. The universe might not be as even-handed as we thought. Whether it's a relic of primordial chaos, a multiverse collision, or something entirely unforeseen, the hemispheric asymmetry reminds us that the cosmos still holds cards it hasn't revealed, and every anomaly is a clue waiting to be deciphered. When we look at the cosmic microwave background, we expect its temperature fluctuations to follow a predictable pattern, a statistical distribution known as Gaussianity. Picture it like the static on an old television screen, random noise with no hidden structure. But what if there's more to the story? Some cosmologists suspect the CMB might contain subtle deviations from this randomness, hints of non-Gaussianity, that could rewrite our understanding of the universe's earliest moments. The hunt for these anomalies isn't just academic. It's a search for cosmic fingerprints left by phenomena we've only theorized about. Inflation, the rapid expansion thought to have shaped the universe, should have produced nearly perfect Gaussian fluctuations, like rolling a die an infinite number of times and getting an even spread of numbers. But if we spot even slight irregularities, say too many sixes or not enough threes, it could mean inflation wasn't as simple or uniform as we've assumed. Perhaps multiple fields interacted during that explosive moment, or cosmic defects like strings, hypothetical, space-time spanning filaments left their mark on the CMB like scratches on a photograph. The data so far is tantalizingly ambiguous. Some analyses suggest faint whispers of non-Gaussianity, particularly in the way hot and cold spots cluster together, while others argue the signal is too weak to confirm. The Planck satellite's findings lean toward the universe being overwhelmingly Gaussian, but with a caveat: there's just enough wiggle room in the margins to keep the debate alive. It's like hearing a distant echo and wondering if it's the wind or a voice too faint to be certain, but too intriguing to ignore. What makes this mystery so compelling is its potential to unlock doors we didn't know existed. If non-Gaussianity is real, it could point to exotic physics, extra dimensions crumpling during inflation, collisions between bubble universes, or even remnants of a pre-Big Bang era. Alternatively, it might reveal that the universe's expansion was driven by something far stranger than a single inflattened field, a cosmic orchestra of forces playing in ways we've yet to comprehend. For now, the question remains open, hanging in the balance between noise and revelation. Future observatories with sharper eyes and finer instruments may finally settle the debate. But until then, the possibility lingers that hidden in the CMB's faint glow are clues not just to how our universe began, but to realities we've yet to imagine. Dark matter is the universe's most enigmatic player, making up roughly 85% of all matter, yet it refuses to show itself directly. We detect its presence through gravity's pull on galaxies and the bending of light, but when it comes to the cosmic microwave background, the evidence should be overwhelming. After all, the CMB is a fossil from a time when dark matter's influence was imprinted on the fabric of spacetime itself. So why haven't we found the smoking gun we expected? This isn't just a minor puzzle, it's a glaring gap in our understanding of how the invisible scaffolding of the cosmos actually works. The CMB's patterns should, in theory, bear the unmistakable fingerprints of dark matter's gravitational dance. During those first critical moments, ordinary matter, protons, electrons, photons, was tightly coupled, a searing plasma too energetic for atoms to form. Dark matter, though, moved to its own rhythm. Unlike normal particles, it didn't interact with light or other forces, meaning it could clump together earlier under gravity's pull, creating dense pockets that shaped the distribution of matter we see today. These gravitational wells should have left subtle distortions in the CMB's temperature fluctuations, a cosmic echo of dark matter's hidden architecture. And yet, when we search for these expected signatures, they're fainter than predicted, like hearing only half of a whispered conversation. One possibility is that dark matter isn't as simple as we've assumed. The leading candidate, cold dark matter or CDM, slow-moving, heavy particles, has dominated theories for decades. But what if dark matter isn't entirely cold? Some models propose a fraction could be warm, lighter and faster, smoothing out those early density fluctuations and leaving a weaker imprint on the CMB. Others speculate about interactions beyond gravity, dark matter particles bumping into each other or even decaying over time, erasing the sharp contrasts we expected to find. It's like trying to reconstruct a puzzle where some pieces have subtly changed shape. Then there's the elephant in the room. Could we be misreading the data entirely? The CMB is a delicate signal, easily muddled by foreground interference, dust from our galaxy, scattered light, even the motion of our solar system. Teasing apart these contaminants to isolate dark matter's true influence is like listening for a single instrument in a symphony of noise. Future missions, like the next generation of CMB telescopes, aim to cut through this fog with unprecedented precision. But until then, the absence of a clear dark matter signature remains a haunting void in our cosmic map. What makes this mystery so profound is what it reveals about our pursuit of the invisible. Dark matter's elusiveness isn't just a technical challenge, it's a reminder that the universe often hides its deepest secrets in plain sight. Every missing signal, every unexplained gap is a clue waiting to be deciphered. And if history is any guide, the answers we eventually uncover might rewrite the rules of physics itself. Deep within the cosmic microwave background's faint glow lies a hidden timeline, one that tells the story of the universe's dramatic rebirth. This is the era of reionization, a cosmic turning point when the first stars and galaxies ignited, flooding space with enough ultraviolet light to tear electrons from atoms and transform the universe from a foggy sea of neutral hydrogen into the transparent cosmos we know today. But here's the puzzle. The CMB's polarization pattern suggests this epoch began startlingly early, raising profound questions about what or who flipped the cosmic lights on so soon after the Big Bang. To understand why this matters, picture the universe as a darkened theater. For hundreds of millions of years after the CMB's release, space was filled with a dense, neutral hydrogen fog, blocking light from traveling far. Then, somewhere around redshift 20, roughly 200 million years after the Big Bang, something changed. The first generation of stars, monsters hundreds of times more massive than our Sun, burst into existence, their fierce radiation ionizing the surrounding gas like a spotlight piercing the darkness. Over time, these bubbles of ionized plasma grew and merged, eventually clearing the cosmic fog entirely. Or at least that's the story our models tell. But the CMB's polarization data paints a stranger picture, hinting that reionization might have begun even earlier, perhaps as early as redshift 15. This discrepancy isn't just a technicality. If reionization truly started that soon, it implies the first stars and galaxies formed in a universe far younger and denser than we'd predicted. Were the earliest stars even more massive and luminous than we've imagined? Or could there have been exotic sources of radiation, primordial black holes, decaying dark matter, or even unknown particle interactions pumping energy into the cosmos before conventional astrophysics says they should have? Some theorists speculate that the universe's infancy might have hosted a population of super-efficient ionizers, objects so bizarre they've since vanished without a trace. Then there's the tantalizing possibility that we're misreading the CMB's signals entirely. The Planck satellite's polarization data, while groundbreaking, is notoriously difficult to interpret. Galactic dust, synchrotron radiation, and even instrumental noise can mimic the patterns of early reionization, leaving room for debate. Future telescopes like the Nancy Grace Roman Space Telescope aim to peer directly into this epoch, hunting for the faintest glimmers of those first galaxies. But until then, the reionization puzzle remains open, a cosmic whodunit where the suspects include everything from hyperactive stars to physics beyond the standard model. What makes this mystery so thrilling isn't just the challenge of fitting the pieces together. It's the realization that the universe's adolescence might have been far wilder than we ever dreamed. Every time we think we've pinned down the timeline of cosmic dawn, the CMB whispers, "Look closer." The answers might rewrite not just the story of the first stars, but the very rules of how galaxies and life itself came to be. Could the cosmic microwave background hold echoes of an era before the Big Bang itself? This is the radical idea at the heart of the phantom cosmic bounce, a theory suggesting that our universe wasn't born from nothing, but instead emerged from the collapse of a previous cosmos. Imagine a cosmic heartbeat, an earlier universe contracting in a big crunch, only to rebound in the explosion we call the Big Bang. If true, the violence of that transition might have left scars in the CMB's patterns, subtle imprints waiting to be decoded. The allure of this idea lies in its defiance of singularity, the notion that the Big Bang marked the absolute beginning of time. Instead, bounce cosmologies propose an endless cycle of expansion and contraction, with each phase leaving faint traces in the next. Some models suggest these echoes could manifest as anomalies in the CMB's temperature fluctuations, unexplained rings, spiral patterns, or even suppressed large-scale correlations like those we've already encountered. It's as if the universe's previous incarnation left behind a shadow, a whisper of its final moments etched into the fabric of our own cosmic dawn. One striking prediction of bounce theories involves the CMB's so-called low multipole alignments. If a prior universe collapsed anisotropically, think of a dying star imploding unevenly. Its final asymmetric crunch could have imprinted a directional bias on the newborn cosmos, explaining phenomena like the axis of evil. Even more provocative is the idea that quantum fluctuations from the pre-bounce era might have survived, carrying information across the rebirth boundary like cosmic driftwood washing up on a new shore. Yet the challenges are immense. Without a full theory of quantum gravity, it's impossible to calculate exactly how a bounce would reshape primordial signals. Critics argue that any pre-Big Bang information would have been scrambled beyond recognition by the extreme energies of the transition. And then there's the observational hurdle. Distinguishing bounce signatures from mundane statistical noise or later astrophysical effects is like trying to hear a single note in a symphony played at the edge of the universe. For all its uncertainties, the phantom cosmic bounce represents something profound, a challenge to our deepest assumptions about time, causality, and the very nature of existence. Whether it's ultimately proven or discarded, the mere possibility invites us to reconsider the universe not as a one-time event, but as a potential chapter in an epic far grander than we've dared to imagine. And that's the real magic of the CMB. It may hold clues not just to our origins, but to realities beyond our own. Everywhere we look in the cosmos, magnetic fields weave through galaxies, stars, and even the vast intergalactic voids. But where did they come from? The cosmic microwave background might hold a clue, revealing faint whispers of magnetism dating back to the universe's first moments. These aren't your everyday magnetic fields. If confirmed, they'd be primordial, a relic from before the first stars ever flickered to life. The implications are staggering. Magnetism might not be the product of cosmic evolution, but something woven into the fabric of reality itself during the Big Bang's fiery dawn. What makes this idea so revolutionary is the timing. Conventional astrophysics suggests magnetic fields arise through dynamo effects, charged particles swirling in galaxies or collapsing stellar cores. But the CMB hints at something far older. Subtle distortions in the light's polarization, like delicate brushstrokes on a canvas, could signal fields that existed when the universe was less than a second old. Imagine finding a fossil predating all known life. That's what we're dealing with here. If these fields are real, they'd imply magnetism was baked into the universe's recipe from the very first ingredients. But how could magnetism survive the Big Bang's chaos? One theory points to phase transitions in the early universe moments when fundamental forces split apart, releasing energy like cosmic aftershocks. These violent shifts might have generated magnetic seeds, tiny knots of energy that inflation then stretched across the cosmos. Another possibility involves exotic particles we've yet to discover. Certain grand unified theories predict that ultra-heavy particles, fleeting products of the universe's extreme youth, could have decayed asymmetrically, leaving behind magnetic imprints as their legacy. The evidence, however, remains tantalizingly indirect. The Planck satellite detected faint, curl-like patterns in the CMB's polarization, a potential signature of primordial magnetism. But the signal is buried in noise, like trying to hear a whisper across a crowded stadium. Skeptics argue it could just as easily be foreground interference or incomplete data modeling. Future experiments like CMB-S4's ultra-sensitive detectors aim to settle the debate by mapping these patterns with razor-sharp precision. If confirmed, primordial magnetism would rewrite cosmic history. These fields could have shaped the first galaxies, guided the collapse of matter, even influenced the formation of life's building blocks. More profoundly, they'd hint at physics operating at energies so extreme our particle colliders can't touch them, a window into the universe's most fleeting, violent instants. Whether the signal is real or not, the hunt itself reveals something essential. The CMB isn't just a relic of the past, it's a detective's notebook filled with cryptic clues waiting to crack the case of how everything began. The cold spot's chilling mystery deepens when we confront a glaring cosmic contradiction. If this colossal cold patch in the CMB were truly caused by a supervoid, an enormous, matter-scarce region stretching billions of light-years, we'd expect galaxy surveys to reveal a corresponding emptiness. Yet when astronomers scour the suspected area, the void they find is far too small and shallow to account for the temperature drop. It's like hearing an orchestra tuning up, only to peek behind the curtain and find a lone violinist. This mismatch between prediction and observation has cosmologists questioning whether we've misunderstood the very nature of voids, or if something far stranger is at play. Voids aren't just empty space, they're dynamic players in cosmic evolution. As light traverses these underdense regions, it loses energy climbing out of their gravitational wells, a process called the integrated Sachs-Wolf effect. Normally, this energy loss is subtle, but for the cold spot to appear as pronounced as it does, we'd need a void so vast it would dwarf any structure seen in the nearby universe. The problem: the largest confirmed void in the cold spot's direction, the Eridanus supervoid, spans merely 500 million light-years, nowhere near the 2 billion light-year behemoth required. Even stranger, its density deficit is only about 30% below average, making it cosmically underwhelming compared to the profound chill it's supposedly causing. Could our models of void physics be incomplete? Some theorists suggest these cosmic deserts might harbor hidden complexities, perhaps exotic dark energy dynamics or unknown large-scale interactions amplifying their gravitational shadows. Others propose that multiple smaller voids aligned along our line of sight could mimic a single giant void's effect, like stacking magnifying glasses to intensify sunlight. But detailed simulations struggle to reproduce the cold spot's extreme profile through these mechanisms alone. The numbers simply don't add up. Then there's the possibility that we're being misled by cosmic selection bias. Our galaxy surveys map only the relatively nearby universe, leaving earlier epochs unexplored. If an ultra-distant void exists beyond current observational limits, one so ancient its light hasn't reached us yet, it could theoretically imprint the cold spot without leaving a visible trace in modern sky maps. It's a tempting explanation, but it stretches conventional cosmology to its breaking point, requiring voids of unprecedented scale or bizarre evolutionary paths. The most thrilling alternative, the cold spot might not be a void's shadow at all, but evidence of a cosmic defect, a topological kink in space-time left over from the universe's violent birth. Certain grand unified theories predict that as the early cosmos cooled, cracks might have formed in its structure, like ice fracturing as it freezes. These defects could have generated gravitational distortions capable of imprinting anomalous cold regions on the CMB. If true, the cold spot wouldn't be an absence but a scar, a remnant of physics operating at energies we can't begin to replicate on Earth. What makes this enigma so compelling is its refusal to fit neatly into any box. With each observation, the missing supervoids problem forces us to reconsider not just voids, but the fundamental interplay between light, gravity, and the large-scale structure of reality itself. Whether it's flawed models, unseen voids, or exotic relics from creation, the cold spot stands as a stark reminder. Sometimes the universe's loudest mysteries come from what we don't find. Tucked within the cosmic microwave background's subtle temperature variations lies a geometric oddity that sparked fierce debate: faint concentric circles stacked like ripples in a pond. These purported patterns, first identified in 2007 by a team analyzing WMAP satellite data, don't match the random fluctuations we'd expect from standard cosmology. Instead, they appear unnaturally regular, almost as if the universe had been struck multiple times by some colossal, reverberating force. For proponents of the cyclic universe theory, these circles aren't just artifacts. They're cosmic bruises, evidence that our universe has collided with others in a vast multiverse over and over again. The idea hinges on a radical reimagining of time and space. In cyclic models, the Big Bang wasn't a singular event, but one in an endless series, each triggered by a collision between four-dimensional branes or membranes floating in higher dimensional space. Picture two sheets of paper drifting toward each other in a breeze. When they meet, the impact releases enough energy to birth a new universe, complete with its own CMB. These collisions wouldn't be one-time affairs. They'd recur rhythmically, leaving behind circular imprints in the CMB where the brain's energy bled into our cosmos. The circle's spacing could even encode the timeline between collisions, turning the CMB into a cosmic clock ticking across eons. Skeptics, however, aren't convinced. Independent analyzers of Planck satellite data failed to replicate the circles at the same statistical significance, suggesting they might just be flukes, random fluctuations masquerading as structure. The human brain excels at finding patterns even when none exist. A phenomenon called pareidolia, like seeing faces in clouds. Could the same be happening here? Then there's the challenge of distinguishing primordial signals from foreground noise. Dust in our own galaxy, gravitational lensing, even the echoes of galaxy clusters can sculpt the CMB's light in ways that mimic concentric rings without invoking radical physics. Yet the possibility lingers. If these circles are real, they'd imply a cosmos far stranger than we've imagined, one where universes bounce, collide, and rebirth in an infinite dance. Future CMB experiments with sharper resolution could settle the debate, either confirming the patterns as scars of a multiverse or relegating them to the annals of cosmic illusions. Until then, these ghostly circles remain a tantalizing what-if, a reminder that the universe's oldest light might still hold secrets we've only begun to trace. Among the cosmic microwave background's most unsettling puzzles is a phenomenon so strange it defies conventional cosmology. Entire galaxy clusters streaming toward a single point in space as if pulled by an unseen hand. Astronomers call this dark flow, and if real, it hints at forces operating far beyond the observable universe, perhaps even other universes exerting their gravity on ours. The implications are staggering. Imagine tossing a handful of leaves into a river and watching them all drift in the same direction despite the current's chaos. That's the essence of dark flow, a coordinated motion where none should exist. The discovery emerged from meticulous studies of galaxy clusters, the universe's largest gravitationally bound structures. By measuring the subtle shifts in the CMB's temperature as it passed through these clusters, a phenomenon called the kinetic Sunyaev-Zeldovich effect, researchers noticed something eerie. Hundreds of clusters, some billions of light-years apart, appeared to share a common velocity, moving toward a patch of sky near the constellations Centaurus and Hydra at speeds exceeding 600 kilometers per second. That's fast enough to cross the continental United States in under 7 seconds. The kicker: this motion couldn't be explained by the known distribution of matter in our universe. It was as if an enormous, invisible magnet lay beyond the cosmic horizon, tugging everything toward it. Critics were quick to pounce. Could this be a systematic error, a quirk of data interpretation? The Planck satellite's later analyzers failed to confirm the signal at the same strength, fueling skepticism. Yet, intriguingly, it didn't entirely rule it out either. Some studies suggest the flow might extend even farther than initially thought, implicating superclusters over half the observable universe's width. If true, the scale of whatever's causing this would dwarf anything in our cosmological playbook, requiring a structure or force so vast it challenges the very principle that the universe should look roughly uniform at large scales. The most electrifying explanation, dark flow, could be the gravitational fingerprint of another universe. In certain multiverse models, our cosmos is just one bubble in an endless froth of universes, each with its own physical laws. If a neighboring bubble passed close enough during inflation, its gravity might have imprinted a directional tug on our matter, persisting like a cosmic wake rippling through time. Alternatively, the flow might trace back to irregularities in the pre-inflationary universe, ancient defects in spacetime's fabric that never fully smoothed out. Yet the mystery endures because it sits at the edge of testability. The suspected source of the pull lies beyond the cosmic horizon, forever out of reach. Future observatories could sharpen the measurements, but for now, dark flow remains a tantalizing what if, a reminder that the universe's greatest enigmas often lie just beyond the limits of our vision. Whether it's a statistical ghost, a flaw in our models, or a window into the multiverse, one thing is clear: the cosmos still holds mysteries that defy even our boldest theories. The universe's infancy was a time of unimaginable chaos, a seething plasma where the fundamental forces we know today were still fused into a single, unified power. As this primordial soup cooled, theorists predict it should have cracked under the strain, leaving behind cosmic scars called topological defects. These aren't your everyday blemishes. We're talking about spacetime spanning cosmic strings, domain walls thicker than galaxies, and textures woven into the fabric of reality itself. Grand unified theories which attempt to merge electromagnetism with the strong and weak nuclear forces insist these defects must have formed during the universe's earliest phase transitions. Yet when we scour the cosmic microwave background for their fingerprints, we find nothing. It's as if the universe tidied up all its cracks before we could take a picture. Cosmic strings, the most famous of these defects, would be unimaginably dense filaments thinner than a proton, but with the mass of a mountain range packed into every mile. Stretching across the cosmos, their gravity would warp spacetime around them, creating telltale kinks in the CMB's temperature patterns, sharp, linear discontinuities unlike anything produced by random fluctuations. Domain walls, meanwhile, would carve the universe into discrete regions with different physical properties, leaving stark boundaries in the CMB's polarization. And textures, these would manifest as spiral hotspots, swirling imprints of twisted spacetime. The problem: after decades of searching with increasingly sensitive instruments, none of these signatures stand out against the CMB's noise. The defects we've been promised are conspicuously absent. So where did they go? One possibility is that inflation, that brief period of exponential expansion, smoothed them away before they could leave a lasting mark. Think of it like stretching a crumpled sheet of paper until every wrinkle disappears. If inflation lasted just a fraction longer than we've assumed, it could have erased all traces of defects by diluting them across scales too vast to observe. Alternatively, the phase transitions that birthed these defects might have occurred more smoothly than predicted, avoiding the cosmic snapping that would have produced them. Some supersymmetry models suggest extra particles could have acted as cosmic lubricants, preventing spacetime from fracturing entirely. Then there's the unsettling third option. Maybe our grand unified theories are missing something fundamental. The absence of defects implies the early universe's symmetry, breaking the separation of forces, happened in a way that left no ragged edges. This would require an astonishingly precise alignment of energies and temperatures, almost as if the cosmos conspired to clean up after itself. For theorists, this fine-tuning is deeply unsatisfying. Nature rarely ties up loose ends so neatly. It's like walking into a demolition site and finding every brick stacked in perfect rows. The search isn't over. Some researchers are chasing subtler defect signatures, like faint gravitational wave backgrounds that could ripple from oscillating cosmic strings. Others are re-examining the CMB's most anomalous features, wondering if defects might be hiding in plain sight, masquerading as statistical noise. But for now, the silence is deafening. Whether it's a clue about inflation's duration, a flaw in our unification models, or a hint of physics beyond our grasp, the missing defects remind us that the universe's earliest moments might have been far more elegant or far stranger than we ever imagined. One of the most persistent headaches in modern cosmology isn't a missing piece of the puzzle. It's a glaring mismatch between two ways of measuring the universe's expansion. On one side, we have the cosmic microwave background, which suggests the cosmos is expanding at about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and galaxies peg the rate closer to 73. This discrepancy, known as the Hubble tension, might seem like a minor accounting error, but it's grown too large to ignore. What if the CMB is trying to tell us there's more to cosmic expansion than we've assumed? The crux of the problem lies in how these measurements are made. The CMB's estimate comes from extrapolating backward using the precise patterns of temperature fluctuations to reconstruct the universe's early conditions, then letting our models of cosmic evolution calculate how fast space should be stretching today. Meanwhile, local measurements rely on direct observations of celestial objects like Cepheid variable stars and Type Ia supernova, whose distances and redshifts can be painstakingly calibrated. Both methods are meticulous, both are backed by Nobel Prize-winning science, and yet they stubbornly refuse to agree, the odds of this divergence being a fluke. Less than 1 in a million, that's not tension, that's a full-blown crisis. So where does the disconnect come from? One tantalizing possibility is that our models of the universe's ingredients are incomplete. The CMB's calculations depend heavily on the assumed amounts of dark matter and dark energy, the invisible scaffolding and mysterious force driving cosmic acceleration. If either of these is behaving differently than we've assumed, say, dark energy's strength has changed over time, or dark matter interacts with itself in ways we haven't accounted for, it could skew the expansion rate derived from the early universe. Imagine baking a cake where you misjudge the leavening agent. The final product won't rise as expected, no matter how precise your oven temperature. Then there's the wild card, early dark energy. Some theorists propose that a fleeting form of extra energy might have briefly surged during the universe's first few 100,000 years, subtly altering the CMB's imprint without leaving other traces. This phantom presence could reconcile the Hubble tension by tweaking the early universe's expansion just enough to align with today's faster measurements. Think of it as a cosmic sprint in the first leg of a relay race, leaving the later runners playing catch-up. But skeptics aren't ready to rewrite physics just yet. Could there be hidden systematic errors in our local measurements? Distance calculations in astronomy are a house of cards. Each rung of the cosmic distance ladder depends on the one below it. If even a single step, like the calibration of Cepheid stars, is slightly off, it could throw off the entire chain. Alternatively, maybe the CMB's models oversimplify the universe's geometry or the behavior of neutrinos. The Planck satellite's data is stunningly precise, but precision doesn't always mean perfection, especially when dealing with something as vast and ancient as the cosmos. What makes this mystery so thrilling is its potential to crack open new physics. The Hubble tension isn't just a disagreement between numbers, It's a flashing neon sign pointing toward gaps in our understanding. Whether it's undiscovered particles, evolving dark energy, or something even more exotic, the solution won't just resolve a discrepancy. It could reveal chapters of cosmic history we didn't know were missing. And that's the heart of science, not the answers we expect, but the questions we never saw coming. When we measure the cosmic microwave background spectrum, it should follow near-perfect blackbody radiation, a smooth curve of light emitted by an ideal object absorbing all energy that hits it. This precise thermal signature was one of the CMB's most triumphant validations, earning COBE satellite scientists a Nobel Prize. But hidden within that smooth profile might be tiny, telltale distortions, minuscule bumps or dips betraying moments when the early universe's plasma was jolted by bursts of unexpected energy. These spectral deviations are like forensic evidence at a cosmic crime scene, hinting at violent events that textbooks never predicted. The hunt for these distortions isn't just academic nitpicking. A flawless blackbody spectrum implies the early universe was a closed system, its photons evolving undisturbed after recombination. But deviations, those suggest something or someone intervened. Imagine a perfectly still pond suddenly rippled by a falling pebble. That's what energy injections would have done. Heated electrons, perturbed photon energies, and left faint scars in the CMB's spectral shape. The culprits could range from annihilating dark matter particles to evaporating primordial black holes, or even the explosive decay of exotic cosmic strings. Each scenario would twist the spectrum in a unique way, offering clues to physics operating at energies far beyond our particle collider's reach. Take the mu distortion, for example. Between roughly 50,000 and 300,000 years after the Big Bang, any sudden energy release like dark matter particles colliding and annihilating would have heated the electron bath just enough to subtly alter photon energies via Compton scattering. The result, a telltale dip in the spectrum around wavelengths of 1 millimeter. Then there's the Y distortion, generated earlier when the universe was so dense that energy injections couldn't fully thermalize, leaving a distinct slope at shorter wavelengths. Together, these distortions could chronicle cosmic violence spanning millions of years, like a geological record written in light. The challenge, these signals are ludicrously faint. Current limits from missions like COBE, Planck, and ground-based telescopes show the CMB's spectrum is blackbody to within a few hundred parts per million. Detecting distortions requires instruments with staggering sensitivity. Think measuring a candle's heat on Earth from the Moon. Upcoming projects like the Primordial Inflation Explorer (PIXI) aim to do just that, scanning the sky with spectrometers precise enough to spot deviations at the parts per billion level. If they succeed, we might uncover energy injections from processes like decaying, sterile neutrinos or even phase transitions in the early universe's vacuum energy, events theorized but never observed. The absence of distortions would be just as revealing. A perfectly pristine spectrum would tighten the noose around exotic physics, ruling out whole classes of energetic early universe phenomena. It's a high-stakes game. Either we find whispers of the cosmos's hidden upheavals, or we confront the eerie perfection of a universe that seems to have played by rules even stricter than we imagined. Whether the distortions are there or not, their pursuit reminds us that sometimes the most profound secrets hide in the slightest deviations, the almost imperceptible tremors in the universe's oldest light. Tucked within the cosmic microwave background's delicate fluctuations lies a clue to one of particle physics' most persistent riddles, the mass of neutrinos. These ghostly particles, streaming through the universe by the trillions every second, interact so weakly with matter that they could pass through light years of lead without a single collision. Yet despite their elusive nature, the CMB bears their imprint, revealing how these cosmic specters shaped the early universe in ways we're only beginning to decipher. The revelation, neutrinos aren't massless as once assumed. but pinning down exactly how much they weigh has opened a Pandora's box of new questions. Here's how the CMB cracks the case. In the universe's first few 100,000 years, neutrinos were anything but passive bystanders. Traveling at nearly the speed of light, they acted like a cosmic pressure washer, smoothing out small-scale density fluctuations through their sheer kinetic energy. This suppression left a distinct signature in the CMB's temperature and polarization patterns, a telltale damping of certain fluctuations that wouldn't exist if neutrinos were truly weightless. By measuring this effect, cosmologists have placed an upper limit on the combined mass of all three neutrino types, roughly 0.1 electron volts at most. That's less than a billionth the mass of a proton, yet it's enough to rewrite the standard model of particle physics. But the plot thickens. While the CMB tells us neutrinos have mass, it can't reveal how that mass is distributed among their three flavors: electron, muon, and tau neutrinos. This hierarchy problem is like knowing a bag contains 3 marbles totaling 10 grams, but having no idea whether one's a 9-gram whopper with 2 tiny companions or 3 roughly equal weights. The normal hierarchy suggests the lightest neutrino is far less massive than the other 2, while the inverted flips the script, proposing 2 heavier ones and 1 ultra-light sibling. Each scenario would leave subtly different fingerprints on the universe's large-scale structure, implications rippling from the Big Bang to present-day galaxy surveys. The CMB's limitations stem from its snapshot of a single cosmic moment. It captures neutrinos' influence during recombination, but can't trace their evolving impact over billions of years. That's where galaxy clustering data steps in. By combining CMB measurements with maps of how galaxies are distributed today, researchers can triangulate neutrino masses with greater precision. The latest results, the sum likely falls between 0.06 and 0.12 electron volts, but the hierarchy remains stubbornly unresolved. What makes this mystery so tantalizing is its reach. Neutrino masses could hold the key to phenomena far beyond particle physics, from explaining why the universe contains more matter than antimatter to shedding light on hypothetical sterile neutrinos that might bridge to dark matter. Some theories even suggest neutrinos gained their mass through interactions with the Higgs field in ways we haven't yet observed, or that their tiny weights are relics from higher dimensional physics. Future CMB experiments like the Simons Observatory and CMB-S4 aim to tighten the constraints by measuring gravitational lensing patterns with nanometer precision. Meanwhile, particle experiments like Dune and Katrin hunt for the hierarchy directly through neutrino oscillations and tritium decay. It's a cosmic detective story where the clues span from the universe's first light to underground labs buried miles beneath the Earth. And with every new measurement, we're reminded, sometimes the smallest things, particles so light they barely register, can tip the scales of our understanding in ways we never saw coming. What if dark energy wasn't a latecomer to the cosmic stage, but a fleeting performer in the universe's earliest act? That's the radical premise of the early dark energy hypothesis, a proposed solution to the Hubble tension that rewrites the timeline of cosmic acceleration. While conventional cosmology pins dark energy's dominance to the last 5 billion years, this idea suggests it might have briefly flared into existence during the universe's first 100,000 years, leaving subtle fingerprints in the CMB before vanishing like a cosmic will-o'-the-wisp. The implications are staggering. This phantom pulse could reconcile the conflicting expansion rates while explaining oddities in the CMB's large-scale patterns, all without overturning our standard model of physics. Here's how it would work. Picture the early universe as a pressure cooker filled with dense plasma and searing radiation. In standard models, this primordial soup expands and cools at predictable rates. But if a short-lived form of dark energy briefly surged during this epoch, it would have given space-time an extra push, like a booster rocket firing during a spacecraft's launch. This temporary acceleration would have subtly altered how matter clumped together in those critical first moments. tweaking the CMB's fluctuation patterns just enough to lower its derived expansion rate. Meanwhile, local measurements unaffected by this ancient burst would still record today's faster Hubble constant, the tension between the two not an error but a clue pointing to an energy surge lost to time. The smoking gun might lie in the CMB's acoustic peaks, the rhythmic pattern of hot and cold spots created by pressure waves rippling through the early plasma. Early dark energy would have dampened these oscillations on specific scales, leaving a telltale suppression in the third peak's amplitude. Intriguingly, Planck's data shows exactly this, a slight deficit in the expected power at these scales, as if something sapped the plasma's energy during a crucial window. Combine that with anomalies like the low quadrupole and hemispherical asymmetry, and suddenly these disparate puzzles start to look like pieces of a single, larger picture, one where dark energy wasn't just the universe's finale, but its opening act. Critics aren't ready to rewrite the textbooks yet. For one, early dark energy must walk a razor's edge, strong enough to tweak the CMB's expansion signature, yet weak enough to avoid disrupting other exquisitely precise measurements like Big Bang nucleosynthesis. It's a cosmic Goldilocks problem. Too much energy would overproduce helium, too little would leave the Hubble tension unresolved. Then there's the question of mechanism. Unlike today's dark energy, often modeled as a cosmological constant, this early variant would need to decay abruptly, like a fuse burning out. Such fine-tuned behavior strikes some theorists as inelegant, though proponents counter that similar phase transitions occur in particle physics all the time. The most thrilling possibility, early dark energy might not be a one-off but part of a recurring cycle. Some models suggest it could represent the first stirrings of the same force now accelerating our universe's expansion. A hint that dark energy has always been present, waxing and waning across cosmic epochs like tides in a celestial ocean. Future CMB experiments armed with ultra-sensitive polarization measurements could hunt for the unique swirls such a scenario would imprint on the early universe's light. Whether it's confirmed or debunked, this hypothesis embodies the most exhilarating aspect of cosmology, the willingness to question even our most cherished assumptions. For decades, dark energy was seen as a modern phenomenon, an architect of the universe's late-life evolution. Now, the CMB whispers that its influence might stretch back further than we ever imagined, challenging us to consider whether the cosmos's greatest mystery has been hiding in plain sight all along. At the smallest scales imaginable, far smaller than an atom, smaller even than a proton spacetime itself may writhe and churn like a turbulent sea. This is the realm of quantum foam, a frothing, fluctuating landscape where the fabric of reality bubbles with virtual particles popping in and out of existence. According to some theories, this foam isn't just a mathematical curiosity. It could have left faint scars on the cosmic microwave background, imprinted during the universe's earliest moments when the cosmos was so small and dense that quantum gravity ruled supreme. If these signatures exist, they'd be whispers from the edge of known physics, evidence that the CMB isn't just a relic of the Big Bang, but a fossil of spacetime's primordial chaos. The idea hinges on a cosmic paradox. Inflation, the universe's explosive expansion, should have stretched quantum fluctuations from the tiniest scales to cosmic proportions. While most of these became the seeds for galaxies and voids, the most minuscule ripples, those born from quantum foam, might have left subtler marks. Picture blowing up a balloon with microscopic cracks on its surface. As it inflates, those cracks stretch into visible patterns. Similarly, if spacetime's quantum jitters were frozen into the CMB during recombination, they could manifest as faint, non-Gaussian distortions, statistical anomalies in the temperature fluctuations that defy classical explanations. Hunting for these signatures is like searching for a single distorted pixel in an ultra-high-resolution image of the sky. The Planck satellite's data has already placed tight limits on non-Gaussianity, but some theorists argue that quantum foam's fingerprints would be far more subtle. perhaps hidden in the CMB's polarization patterns or masked by foreground noise. Certain models predict these imprints would resemble swirling vortices or fractal-like structures, patterns too precise to arise from random chance. Others suggest they might appear as localized hotspots of unexpected correlation, like finding a snowflake in a desert. The challenge: quantum foam operates at scales a trillion times smaller than anything Planck could probe directly. To spot its influence, we'd need CMB measurements of unimaginable precision, capable of detecting deviations in the light's properties at levels approaching 1 part in 10 to the 15th power. Future observatories like CMB S4 or space-based interferometers might reach these sensitivities, but even then, disentangling quantum foam's signal from cosmic variance and instrumental noise would be like listening for a pin drop in a hurricane. Even if the evidence remains elusive, the pursuit itself is revolutionary. Quantum foam's potential imprint on the CMB bridges two of physics' greatest unsolved problems: the nature of gravity at microscopic scales and the origin of cosmic structure. If detected, it would offer the first observational clues to a theory of quantum gravity, validating ideas like loop quantum cosmology or string theory. If absent, it might force us to reconsider whether spacetime's foaminess was ever imprinted on the universe at all, or if inflation erased it entirely, leaving us with a cosmos smoother than our theories predict. What makes this mystery so electrifying isn't just the science, it's the audacity of the question. The CMB, already a portal to the universe's infancy, might also be a looking glass into realms beyond space and time as we know them. Whether quantum foam's whispers are there or not, the search reminds us that the cosmos's oldest light could still hold surprises written in a language we're only beginning to decode. Hidden within the delicate swirls of the cosmic microwave background's polarization patterns might lie one of the universe's most elusive relics, spinning vortices of spacetime itself. These hypothetical whirlpools, known as cosmic textures or primordial vortices, could be scars from a time when the fundamental forces of nature were still untangling themselves. Picture the early universe as a pot of water just beginning to boil. As it cooled, regions of spacetime might have twisted into knots, creating temporary whirlwinds of energy that left faint, spiraling imprints on the CMB's polarized light. If detected, these vortices would be more than just cosmic curiosities. They'd be direct evidence of phase transitions in the fabric of reality, moments when the universe's very rules were rewritten. The hunt for these vortices centers on a unique property of light called B-mode polarization. Most CMB polarization comes from simple, curl-free patterns, like combing a flat field of grass. But vortices would produce a twisting, rotational signature, like whirlpools in that same field. These B-modes are the holy grail for cosmologists, not just because they could reveal textures, but because they might also carry whispers of gravitational waves from inflation. The challenge: distinguishing between the two. While inflation's waves would create a smooth, large-scale B-mode pattern, primordial vortices would leave behind localized, patchy twists, like comparing the ripples from a pebble dropped in a pond to the churning wake of a passing speedboat. Why does this matter? Textures are predictions of grand unified theories, models that attempt to merge electromagnetism with the strong and weak nuclear forces. As the early universe cooled, these forces froze out at different temperatures, like layers of ice forming on a lake. If this phase transition happened unevenly, defects like vortices could have formed, much like cracks spreading through that ice. Their detection would validate decades of theoretical work, proving that the universe's forces really did separate in this dramatic way. But there's a catch. Despite years of searching, from the South Pole Telescope to the Atacama Cosmology Telescope, no definitive vortex signals have emerged. Some argue this absence is itself a clue. Perhaps the phase transitions were smoother than predicted, or inflation stretched the textures so thin they're now undetectable. Others think we're just not looking closely enough. Future observatories like CMB-S4 aim to map polarization with nanometer precision, potentially spotting vortices too faint for current instruments. What makes this search so exhilarating is its stakes. If vortices exist, they'd offer a window into physics at energies 1 trillion times beyond what particle colliders can reach. If they don't, it might mean our grand unified theories need a radical overhaul. Either way, the CMB's polarization isn't just a snapshot of the past, it's a cipher, waiting to reveal whether the universe's infancy was a calm, orderly affair or a tempest of spinning spacetime. And that's the essence of cosmology, decoding the invisible ink written across the sky. Among the myriad candidates proposed to explain dark matter, primordial black holes hold a unique allure. These hypothetical objects, forged in the furnace of the early universe's first chaotic seconds, could have formed from the collapse of ultra-dense regions before stars or galaxies even existed. Ranging in size from a speck of dust to a massive star, they'd be invisible, relentless, and nearly indestructible perfect dark matter contenders. Yet despite decades of searching, the cosmic microwave background remains stubbornly silent about their existence. If these ancient gravitational traps are out there, why hasn't the CMB, our most detailed snapshot of the universe's youth, betrayed their presence? The answer lies in how primordial black holes would have left their mark. In those first critical moments, regions dense enough to collapse into black holes would have also distorted the surrounding plasma, creating hotspots in the CMB's temperature fluctuations. These imprints would resemble cosmic pockmarks, subtle but statistically detectable spikes in the radiation. Even more telling, the gravitational pull of these black holes would have acted like lenses, bending the CMB's light in predictable ways as it traveled across the cosmos. The problem: neither the Planck satellite nor ground-based telescopes like ACT have found evidence of these distortions at the scales predicted. It's as if we've combed through every inch of a crime scene and found none of the fingerprints we expected. One possibility is that primordial black holes simply weren't common enough to dominate dark matter. Simulations suggest they'd need to form within an absurdly narrow window, large enough to survive evaporation via Hawking radiation, yet small enough to avoid gobbling up so much matter that they'd leave glaring voids in the CMB. Hit that Goldilocks zone and they could account for a fraction of dark matter. But the latest constraints from CMB lensing and microlensing surveys suggest they can't be the whole story. If they exist at all, they're lurking at the fringes, making up no more than a few % of the universe's missing mass. Then there's the timing problem. For primordial black holes to explain dark matter, they'd need to form before the CMB's light was set free, during inflation or the quark-gluon plasma era. But the universe back then was a seething, unpredictable place. Quantum fluctuations might have birthed black holes, but they also would have produced a zoo of other exotic particles and structures. The absence of broader anomalies in the CMB suggests that if black holes did form, they did so without dramatically disturbing the cosmic broth, a scenario that requires fine-tuning so precise it borders on the implausible. Perhaps the most tantalizing twist comes from recent theoretical work. Some models propose that primordial black holes didn't just sit idle, they might have clustered into dense halos or even sparked the formation of the first stars. These black hole stars would have burned hotter and died younger, seeding the cosmos with heavy elements far earlier than standard cosmology allows. Intriguingly, astronomers have spotted surprisingly mature galaxies in the distant early universe objects that arguably shouldn't exist unless something jump-started structure formation. Could primordial black holes have been the cosmic accelerant? The CMB's silence might not mean they're absent. It could mean they've been hiding in plain sight, shaping the universe in ways we're only beginning to untangle. For now, the missing evidence remains a gaping hole in the dark matter puzzle. But the hunt isn't over. future CMB experiments armed with sharper resolution and deeper polarization measurements might yet uncover the ghostly fingerprints of these ancient gravitational relics. Or they might force us to confront an even stranger truth, that dark matter isn't just invisible, but fundamentally unlike anything we've imagined. Either way, the silence of the CMB isn't an end, it's a challenge, daring us to listen more closely to the echoes of creation. Among the cosmic microwave background's tapestry of fluctuations, some regions stand out not for their complexity, but for their eerie simplicity. Stretches so smooth they seem almost too perfect to exist. These ultra-smooth patches, some spanning hundreds of millions of light-years, defy expectations from inflationary models, which predict a universe brimming with quantum noise stretched across the sky. Instead, these areas appear oddly muted, like swaths of an otherwise stormy ocean frozen into glassy calm, the odds of such uniformity emerging randomly. Astronomers estimate less than 1 in 10,000. So what could have ironed out these cosmic wrinkles with such precision? Inflationary theory paints the early universe as a quantum carnival, a seething, probabilistic froth where microscopic fluctuations were blown up to cosmic proportions. These ripples should have left the CMB speckled with irregularities at every scale, like static on a television screen. Yet when scientists analyzed Planck satellite data, they found regions where this expected texture all but vanished. One particularly striking example lies near the constellation Eridanus, where temperature variations dip to nearly half the expected amplitude. It's as if someone took an eraser to the universe's blueprint, smoothing away the chaos without leaving a trace. Theories attempting to explain this anomaly range from the conservative to the extraordinary. One camp suggests these patches might be artifacts of cosmic topology. If the universe folds back on itself in a multiply-connected shape, like a three-dimensional torus, certain wavelengths of fluctuations could cancel each other out through interference, creating artificial, quiet zones. Picture the way noise-canceling headphones use opposing sound waves to create pockets of silence. Alternatively, these regions might mark the footprints of pre-inflationary structures, relics from a prior cosmic cycle that somehow survived the Big Bang's reset. If inflation didn't begin everywhere simultaneously, late starting bubbles could have expanded more uniformly, leaving behind islands of unnatural calm. Then there's the spine-tingling possibility that these smooth patches are windows into something beyond our universe. In multiverse scenarios, neighboring bubble universes could have brushed against ours during inflation, their energy fields temporarily suppressing quantum fluctuations where they made contact. The result, cosmic bald spots where the usual turbulence never took hold. It's a speculative idea, but if true, these quiet regions wouldn't just be statistical flukes. They'd be the first observable evidence of a reality vaster than our own. Skeptics counter that the smoothness might stem from something far more mundane, foreground contamination. Our galaxy's dust clouds and the diffuse haze of interstellar electrons can subtly alter CMB measurements, potentially masking fluctuations in certain areas. Yet even after painstaking subtraction of these foregrounds, the anomalies persist, taunting researchers with their quiet defiance. Future observatories like CMB S4 aim to settle the debate with detectors so sensitive they could spot a snowflake in a sandstorm, potentially revealing whether these patches hide new physics or just stubborn noise. What makes these smooth zones so compelling isn't just their existence, it's what they imply about our cosmic blind spots. The very fact that we can't yet explain them suggests inflation, for all its triumphs, might be missing a chapter. Whether it's unseen topology, multiverse collisions, or an entirely new dynamical mechanism, these whispers of order amid chaos remind us that the universe's first moments may have been far stranger than our models dare to suggest. And sometimes the most profound mysteries aren't written in the cosmos's noise, but in its unsettling silence. The cosmic microwave background might be hiding something astonishing, not just clues about our universe, but whispers of others. Among the CMB's anomalies, some researchers speculate that certain irregularities could be the faint bruises left by collisions with other bubble universes in a vast multiverse. Imagine two soap bubbles gently pressing against each other. Where they meet, the membranes distort, leaving a subtle imprint. If our universe inflated alongside others in a higher dimensional space, such a collision could have transferred energy at the boundary, creating a distinctive pattern in the CMB, a cosmic fingerprint from beyond our cosmic horizon. The idea stems from eternal inflation, a scenario where our universe is just one bubble in an endlessly frothing sea of universes, each with its own physics and dimensions. When these bubbles collide, the impact wouldn't be violent like a car crash, but more like a slow, resonant push, a transfer of energy that could leave a circular temperature variation or polarization pattern in the CMB. One of the most searched for signatures is a disk-like anomaly, a ring of slightly warmer or cooler temperatures with sharp edges, unlike the blurry fluctuations expected from random noise. These disks wouldn't match the statistical profile of standard inflationary patterns, making them potential red flags for multiverse activity. The search for these shadows has turned up tantalizing but controversial leads. A team analyzing data from the Wilkinson microwave anisotropy probe claimed to have found 4 unusual circular patches in the CMB, each with edges too crisp to easily dismiss. These regions, dubbed CTC candidates for colliding topological bubbles, showed temperature dips of around 70 microkelvin tiny, but statistically anomalous. Skeptics countered that such patterns could emerge naturally from cosmic variance or foreground interference, like dust in our own galaxy. The Planck satellite's higher resolution data later failed to confirm these features at the same significance, leaving the debate unresolved. But the multiverse hypothesis isn't out of the running yet. Some theorists argue that collisions might leave more subtle imprints, like localized distortions in the CMB's polarization. When two universes brush against each other, the interaction could generate gravitational waves or scalar field perturbations, twisting the polarization of light in specific, detectable ways. Future telescopes like CMB-S4, with their unprecedented sensitivity to B-mode polarization, might finally spot these telltale swirls or rule them out entirely. What makes this idea so electrifying is its audacity. If proven, a single anomaly in the CMB could rewrite our place in reality, proving we're just one universe among countless others, each with its own laws and histories. Yet, even if the evidence never materializes, the pursuit reveals how far cosmology has come, from mapping the glow of creation to hunting for echoes of worlds beyond our own. Whether these shadows are real or cosmic mirages, they remind us that the universe's deepest secrets may lie not in what we see, but in what we've yet to imagine. Einstein's theory of relativity rests on a revolutionary idea. There's no privileged frame of reference in the universe. The laws of physics should work the same whether you're standing still or hurtling through space at near light speed. But the cosmic microwave background seems to whisper a different story, one where the universe itself might have a favorite direction. This controversy centers on the CMB dipole, a lopsided pattern in the sky where one hemisphere glows slightly warmer than the other, as if the entire cosmos is moving through some invisible medium. At first glance, it's easy to dismiss as just our solar system's motion through space, but dig deeper, and this anomaly threatens to upend one of modern physics' most sacred principles. The dipole was one of the first features discovered in the CMB way back in the 1970s. Scientists assumed it was straightforward. The Milky Way is moving at roughly 630 kilometers per second relative to the CMB's rest frame, creating a Doppler shift that blue shifts light in the direction we're heading and redshifts it behind us. This explanation neatly fits our understanding of galaxy motions within the cosmic web. But here's where things get weird. When astronomers tally up the gravitational pulls of all known structures, the Great Attractor, the Shapley supercluster, even Dark Flow's mysterious tug, they can only account for about half of this velocity. The rest a cosmic mystery. Some theorists propose an even more radical interpretation. What if the dipole isn't just about our motion, but reveals a deeper asymmetry in the universe itself? Certain modified gravity models like tensor vector, scalar gravity, or emergent gravity suggest space-time might have subtle directional preferences on cosmological scales, like invisible cosmic currents that subtly steer matter. Even more provocatively, some quantum gravity approaches hint that the vacuum of space-time could have a preferred frame at ultra-large scales, a relic from the universe's quantum origins. If true, the CMB dipole wouldn't just be a speedometer for our galactic journey, it'd be a compass pointing toward physics beyond Einstein. Skeptics counter that extraordinary claims require extraordinary evidence. The dipole's alignment with our motion is too precise to ignore, and alternative explanations often introduce more problems than they solve. Perhaps undiscovered superstructures beyond our observational horizon are tugging on us, or local voids are skewing our measurements. Even the Planck satellite's painstaking maps haven't settled the debate. They've only deepened the uncertainty by revealing secondary anomalies in the dipole's higher-order multipoles, subtle wrinkles that don't quite fit the standard kinematic story. What makes this mystery so electrifying isn't just the potential violation of relativity. It's the realization that the CMB, our most pristine map of the cosmos, might still hold clues to regimes of physics we've never directly observed. Whether the dipole is a mundane speed bump or a cosmic stop sign, it challenges us to question whether the universe truly plays by the rules we've written, or if we've just been reading the wrong page of the manual. And that's the heart of science, not defending old truths but chasing new ones, no matter how unsettling they may be. Among the cosmic microwave background's greatest unsolved puzzles is the absence of something we're almost certain should be there: cosmic strings. These hypothetical flaws in space-time, predicted by grand unified theories, would be unimaginably thin yet denser than neutron stars, stretching across the universe like cracks in frozen ice. As the early cosmos cooled, phase transitions in its fundamental forces should have trapped energy into these one-dimensional defects, leaving behind a network of cosmic spaghetti woven through the fabric of reality. Yet despite decades of searching through the CMB's intricate tapestry, not a single definitive string signature has emerged. Their absence isn't just a minor oversight, it's a direct challenge to our understanding of how the universe stitched itself together. The mystery deepens when we consider how obvious these strings should be in the CMB. Picture a violin string vibrating under tension. Cosmic strings would similarly oscillate as they slice through space, emitting bursts of gravitational waves and creating sharp, linear discontinuities in the CMB's temperature map. These kinks would stand out starkly against the background's Gaussian noise, like a knife's edge cutting through fog. Even more telling, moving strings would produce double images of distant galaxies through gravitational lensing, an effect so distinctive it would be nearly impossible to mimic with ordinary cosmic structures. The Planck satellite's exquisite maps had the resolution to spot these anomalies, so why haven't they shown up? One possibility is that inflation. The universe's explosive early expansion stretched these defects beyond detectability. Just as smoothing a crumpled bed sheet removes wrinkles, inflation may have diluted cosmic strings to scales so vast their signatures vanished into the CMB's statistical noise. Alternatively, the strings might still be there, but so light and low energy that their gravitational footprints are too faint for current instruments to catch. Some supersymmetry models suggest extra dimensions or exotic particles could have softened the phase transitions that created them, producing fewer defects than classic theories predict. It's like expecting shattered glass but finding only a few hairline fractures, a puzzle for any detective. Then there's the unsettling third option. Maybe our grand unified theories are missing a crucial piece of the puzzle. The absence of cosmic strings hints that the early universe's symmetry, breaking the separation of fundamental forces, happened far more smoothly than physicists anticipated. This would require a level of cosmic finesse that borders on the miraculous, like a phase transition so flawlessly executed it left no debris behind. For theorists who expected the universe's infancy to be a messy, violent affair, this cleanliness is deeply suspicious, almost as if something swept away the defects before they could imprint on the CMB. Yet the hunt isn't over. While the CMB hasn't delivered smoking gun evidence, other avenues remain open. Pulsar timing arrays, which monitor the precise rhythms of spinning neutron stars, could detect the gravitational wave background from a network of oscillating strings. Future space-based interferometers like LISA might spot the ripples from string loops evaporating in distant galaxies. And some researchers still comb through the CMB's most anomalous features, wondering if strings might be hiding in plain sight, disguised as statistical flukes or foreground interference. What makes this absence so profound is what it reveals about our cosmic blind spots. The missing strings aren't just a theoretical hiccup, they're a reminder that the universe's infancy may have been far more orderly or far stranger than our models can explain. Whether it's inflation's hidden erasure, undiscovered physics, or simply strings too subtle to see, their silence speaks volumes about how much we still don't know. And in that quiet, there's a tantalizing question. If the universe left no strings attached, what other rules did it break along the way? The cosmic microwave background is more than a relic of the Big Bang. It could be the Rosetta Stone for decoding quantum gravity, the elusive theory meant to unite Einstein's relativity with the bizarre rules of the quantum world. Hidden within its faint temperature fluctuations and polarization patterns might be whispers of spacetime's granular structure, echoes from an era when the universe was so small and dense that gravity itself played by quantum rules. If these signatures exist, they'd rewrite physics, offering our first observational window into a realm where time and space cease to be smooth and continuous, instead fracturing into a seething foam of uncertainty. To grasp why the CMB holds this potential, picture the universe in its first sliver of existence, a trillionth of a second old, compressed into a space smaller than a single atom. At these scales, quantum fluctuations in spacetime itself would have been as real as ripples on a pond. Inflation, that explosive expansion, would have stretched these microscopic tremors to cosmic proportions, freezing them into the CMB's patterns like fossils in amber. The catch: standard models assume spacetime was smooth during inflation. But if quantum gravity's predictions hold, there should be subtle deviations, tiny, non-random kinks in the CMB's temperature and polarization that betray the granularity beneath. The most promising place to hunt for these anomalies is in the CMB's B-mode polarization, the twisting patterns that could carry imprints of primordial gravitational waves. Quantum gravity theories like loop quantum cosmology predict these waves would have unique statistical signatures, perhaps a preferred directionality from spacetime's inherent discreteness, or an unexpected cutoff in their frequency spectrum. Imagine listening to a symphony where one instrument plays slightly out of key. That's the kind of telltale discord researchers are searching for. Some models even suggest that spacetime's quantum foam could have lensed the CMB's light in peculiar ways, leaving behind fractal-like distortions or anomalous hot spots too precise to be random. Yet the challenge is staggering. Quantum gravity's effects, if they're there at all, would be buried under layers of cosmic noise, drowned out by the CMB's own complexity. It's like trying to hear someone whisper across a crowded stadium while wearing earmuffs. Current telescopes lack the sensitivity to spot these whispers, but next-generation observatories like CMB-S4 and the proposed PICO satellite aim to change that. With detectors colder than interstellar space and resolutions sharp enough to map polarization at arc-minute scales, they could finally tease out whether the universe's oldest light carries these ghostly fingerprints. What makes this search so electrifying is its stakes. If successful, it wouldn't just confirm one theory of quantum gravity, it could rule out others. String theory's higher dimensions, for instance, might leave different imprints than loop quantum gravity's spin networks. Even a null result would be profound, forcing theorists back to the drawing board to explain why spacetime's quantum nature left no trace. Either way, the CMB is more than a relic. It's a bridge between the universe we see and the hidden physics that shaped it, waiting for us to learn how to listen. Gravitational lensing should warp the cosmic microwave background in predictable ways, like light bending through a funhouse mirror, distorting the CMB's temperature and polarization patterns as it travels across the universe. According to general relativity, the gravitational pull of massive structures, galaxies, dark matter halos, even entire superclusters, ought to subtly twist this ancient light, leaving a telltale smearing effect that scientists can measure. But here's the puzzle. When researchers tally up the lensing signal in high-resolution CMB maps, it's noticeably weaker than our best cosmological models predict. The discrepancy isn't huge, just a few percentage points, but in a field where precision reigns supreme, even a slight mismatch can hint at something fundamental we've overlooked. One leading explanation dives into the nature of dark matter itself. If dark matter behaves differently than our cold, collisionless standard model assumes, say, if it interacts with itself or other particles through some unknown force, it could alter how structures grow over cosmic time. Picture a crowd of invisible dancers subtly changing their steps. Their movements would reshape the gravitational landscape, potentially weakening the lensing effect on the CMB. Warm dark matter, a hypothetical lighter cousin to standard dark matter, would also suppress small-scale clumping, leading to fewer dense regions to bend light. The result, a smoother lensing signal, just as we're observing. But dark matter isn't the only suspect. Neutrinos, those ghostly particles flooding the cosmos, could also be playing tricks on us. Recent experiments confirm that neutrinos have mass, and if that mass is higher than currently estimated, their sheer abundance could have smoothed out matter fluctuations in the early universe. Think of them as cosmic sandpaper, gently erasing the sharpest gravitational wrinkles that would later lens the CMB. Alternatively, the answer might lie in the way we model the universe's expansion. If dark energy's strength varied over time, or if gravity itself deviates from Einstein's predictions on cosmic scales, it could tweak the growth of structures just enough to explain the lensing anomaly. Then there's the elephant in the room. What if we're misreading the data? Measuring CMB lensing is a staggering technical feat, requiring exquisitely precise maps of both the CMB's faint distortions and the distribution of matter across billions of light years. Contaminants like galactic dust or the thermal haze of galaxy clusters can mimic or mask lensing signals, muddying the waters. Even the algorithms used to reconstruct lensing from raw data carry inherent uncertainties, leaving room for subtle biases. Future experiments like CMB-S4, with detectors 10 times more sensitive than current arrays, aim to cut through this noise, but for now, the weakness of the lensing signal remains an open question. What makes this mystery so compelling is its reach. The CMB's lensing isn't just a curiosity, it's a direct probe of how gravity and matter conspire to shape the cosmos. If the discrepancy holds, it could force us to reconsider everything from the nature of dark matter to the validity of relativity itself. Whether it's unseen particles, tweaked gravity, or simply a cosmic illusion, the CMB's unexpectedly gentle lensing reminds us that the universe still has cards up its sleeve, and every anomaly is a chance to play a new hand. Right now, the cosmic microwave background bathes the universe in a faint but detectable glow, a whisper of heat left over from the Big Bang, but this primordial light isn't eternal. Every passing second, as the cosmos expands and stretches space-time like an infinite rubber sheet, those microwaves redshift further, their wavelengths growing longer, their energy seeping away into the cold void. Billions of years from now, the CMB will fade entirely, its signal dissolving into undetectable radio silence. And when that happens, it won't just mark the end of an era, it'll reveal something profound about the ultimate fate of everything. Picture a universe so old that every star has burned out, every black hole has evaporated, and the very fabric of space has stretched so thin that atoms themselves begin to unravel. This is the heat-death scenario, a distant future where entropy reaches its maximum, and the cosmos becomes a uniform, lifeless sea of particles too diffuse to interact. In this frigid eternity, the CMB's disappearance would be one of the last observable milestones, its photons stretched to wavelengths longer than the observable universe itself. Without it, future civilizations, if any still exist, would have no window into the universe's fiery birth. The Big Bang's afterglow, our most direct link to creation, would vanish forever, leaving behind only the dim echoes of dark energy's relentless push. But what if heat-death isn't the only possibility? Some theories suggest the CMB's fading could hint at a far stranger destiny. In cyclic cosmologies, where the universe endlessly collapses and rebounds, today's redshifted microwaves might one day blueshift back into visibility, heralding a new Big Bang. Imagine the CMB not as a dying ember, but as a hibernating signal, a cosmic seed waiting for the right conditions to reawaken. Even wilder are ideas like conformal cyclic cosmology, where the universe's infinite expansion somehow resets itself, transforming the CMB's stretched photons into the seeds of a new primordial fireball. In these models, the CMB's disappearance isn't an end but a prelude to rebirth. Then there's the unsettling third option, that the CMB's fade out will reveal gaps in our understanding of spacetime itself. If dark energy's strength changes over time, accelerating expansion even faster, it could rip apart the universe in a big rip, shredding galaxies, stars, and even spacetime before the CMB fully fades. Alternatively, if the vacuum of space decays into a lower energy state, the CMB's spectrum could abruptly distort, a final cosmic SOS before reality rewrites its own rules. These scenarios aren't just speculative, they're testable. By tracking how the CMB's temperature and polarization evolve over eons, we might catch early warnings of the universe's true trajectory. What makes this mystery so haunting is its inevitability. Whether the CMB's end comes with a whimper, a bang, or something beyond our imagination, its fading light forces us to confront a startling truth. The universe isn't just expanding, it's evolving, transforming, and perhaps even recycling itself in ways we've barely begun to grasp. And long after its last photon winks out, the CMB's legacy will linger in the deepest questions it leaves behind, not just about where we came from, but where we're ultimately headed. From the cosmic microwave background's faint whispers to its puzzling asymmetries, each of these 30 mysteries peels back another layer of the universe's deepest secrets. Consider the cold spot, a cosmic bruise that could be a supervoid shadow, a collision with another universe, or even a crack in spacetime itself. Then there's the eerie alignment of the axis of evil, defying our assumption that the cosmos has no preferred direction. The missing supervoids, the vanishing large-scale correlations, the phantom echoes of a pre-Big Bang bounce, each anomaly forces us to question whether we've misunderstood inflation, gravity, or even the nature of reality. These puzzles aren't just academic curiosities, they're the edges of our cosmic map, the places where the known universe frays into the unknown. Take dark flow, where entire galaxies race toward an unseen horizon. Could it be the gravitational pull of a reality beyond our own, or the spectral distortions hiding in the CMB's perfect blackbody glow, hinting at violent energy injections from dark matter annihilations or primordial black holes evaporating into the void? Even the absence of cosmic strings, those space-time scars we're certain should exist, whispers that the early universe might have been far smoother or far stranger than our theories predict. And let's not forget the grandest enigma of all, the CMB itself, a fading echo that will one day vanish entirely, leaving future civilizations with no trace of the Big Bang's fireball. Will its disappearance mark the heat death of everything, or could it be the prelude to a cosmic rebirth? Every mystery we've explored, from the hemispheric power asymmetry to the quantum foam's elusive fingerprints, is a reminder that the universe is still writing its story, and we've only just begun to read it. So here's the call to adventure: keep questioning. The next breakthrough might come from a telescope not yet built, a theory not yet imagined, or even from you staring up at the night sky and wondering what else is out there. The cosmos is far weirder, messier, and more magnificent than we've dared to suppose. And as long as the CMB's light still reaches us, the mysteries and the discoveries are just beginning. Stay curious.